Welcome back to Island Biogeography. Rebuilding this video, trying to make it shorter and faster today. So let's take a look. This is MacArthur and Wiltord's equilibrium theory of island biogeography. The core here is that the goal of the theory is to predict the number of species on an island as a function of ecological processes. And MacArthur and Wiltord boiled this down to the processes of colonization, which we see here, and extinction. All right, so I want you to think of this first in the big picture as like a bucket of water. So I draw this, I'm going to highlight this section as my bucket here of water. And I think about the number of species inside, which is written as S, the species richness, right? And as the amount of water you can fit in the bucket. So if you start filling it with colonization, you can think of this sort of fire hose of colonization coming in. And then what we see is that, of course, it fills up the bucket. So we increase S until it reaches the top of the bucket, which is right around here somewhere, and then pretty soon the water starts pouring out the other side, and that is analogous to the concept of extinction. So you get too many species in there, you start losing them. If you don't have that many species and you add some colonization, the number will increase. Now let's take a look. Now I know I've got everything written on this graph already, but let's take a look at it. Again, I'm going to use my highlighter to draw your attention to certain areas. The colonization rate on the left-hand side is the rate of colonization. Now, this is a rate of new species reaching the island and settling on the island. It's not just the rate of getting there, it's also the rate of successfully colonizing the island. Okay? The extinction rate on the right-hand side is the rate at which they go extinct, pretty straightforward. And of course, on the x-axis at the bottom, we have species richness, right? And the species richness number down there is actually number of species. So on the left-hand side by the 0, we have few species down here, which is near 0, and we have many species on this end, which I write again. I've got the word many there already, so I'll scratch that out. All right, let's look at two things. If we look at the colonization rate, we see the slope is negative, and that slope is going to be declining there. Now, we make sure we label that, all right? So this is going to be labeled colonization. If you just put it on the vertical axis, over here, I don't know which line you're referring to. So let's make sure you label it. And then you write slope is caused by something. So in this case, you got to think of that we're eliminating all the things like size of island, distance of island from mainland, all that stuff's going away, latitude, all that goes away until we look at just what's on the graph. What's on the graph is species richness, extinction, and colonization. So why would the colonization rate change with species richness? So species richness in this way has to be causative in some way. And it turns out that, of course, I've got it written on here that competition for resources increases with S. So that means there are less resources for new colonizers. So the more species already present, there basically isn't enough elbow room for new species that are coming in. So the more that are there, the lower the rate of colonization. As we look to the extinction side over here, what we see is there are two explanations for the slope of that curve. And again, both are directly dependent on the number of species. The first one is that when there's more species on the island, there's more competition and more competitive exclusion due to limited resources. So competitive exclusion will increase the extinction rate. The second one that I have here is that with increased S, the number of species, each species must by definition, have a smaller population size because there's a limited amount of space and resources on the island. So that means that population size is smaller, which means all the problems associated with having a smaller population will be in effect. So those hazards are there. So like the Ali effect, which we've talked about, and demographic stochasticity, both will increase the rate of extinction. So those two things together, and I'm going to go ahead and use my green. This is our equilibrium point. Keep in mind for the equilibrium point, the equilibrium point is actually down here on the x-axis, the number of species, that is the equilibrium number of species. If the number of species drops below that, so if S were to be down here somewhere like that, then what you would see is you would see a relatively low extinction rate and you'd see a high colonization rate. Going back to my bucket, you'd see a lot more colonization going on than extinction, so the amount of water would increase in the bucket, which would mean that the S would actually float back up to that equilibrium level of S. So you wouldn't be able to stay in either of these points. And the same thing would happen to a higher S. You would have higher extinction rates up here, and so you would actually converge back to this equilibrium level S. And that is the island biogeography model with all of its components that you need for class. Please check part 2 to see what